Okay, let's begin. Yeah, so in this session, we will look at circuits which are basically used to discriminate the sign of two inputs. That's basically comparator. So what you expect out of a comparator is, if you have two signals, Vi plus and Vi minus, the output should be 0 if Vi plus is less than Vi minus. It should be 1 if Vi plus is greater than Vi minus. Okay, in principle, it's not defined for if Vi plus is exactly equal to Vi minus, the output is basically becomes a metastable state. We'll not get into the discussion of metastability and all. We'll assume that the comparator resolves either to +1 or -1. Now this 1, 0 itself could be represented as 0 volts and 1 could be represented as VDD. Okay, depending on the type of circuit design, you could have different representations of the logic level for 0 and 1. But let us stick to the simplistic one, which is basically 0 and VDD. So input is continuous, output is digital. It's either 0 or 1. So how can we design such a circuit which gives you a digital output for a continuous or a analog input? So one way would be, of course, you can use an amplifier which has a very high gain, like how we have seen in the previous session, what is known as op amp as a comparator. So you can use an amplifier which has very high gain, and it will basically for us if the gain is really very high, for a very small input also your output will be saturated. But that is something which is not always practical, and getting very high gain by using multi-stage amplifiers eventually also implies that your latency will increase between the input and the output. Okay, so one of the ways of getting very high quick decisions without using very high gains or multi-stage amplifiers is by using what is known as positive feedback. Okay, so if I have a, let me say, some kind of transconductor, and I use two such transconductors in positive feedback, and let me say one node is Vi minus and the other node is Vi plus. There will be some capacitance either deliberately put or parasitic capacitance on both these nodes. For now, let us assume they're equal. This, even if you take two simple a simple latch, basically two inverters connected in feedback, this also behaves like two transconductors if when the difference between Vi plus and Vi minus is small. Okay, so if you look at this, the inverter characteristics looks something like this, right? V0 versus Vi. So when I have another inverter, V0 of one is Vi of the other. Therefore, the other one will look like this. So this is what the simple SRAM butterfly diagram that you might all have come across looks like, right? So in the vicinity of Vi plus being all close to Vi minus, in this vicinity of Vi plus being close to Vi minus, this circuit behaves something, or the equivalent circuit looks is same as what is run to the left here, with two transconductors connected in positive feedback. Okay, so now let us see how the output changes, or how the output evolves, if I have to be right, when you have such a circuit with some initial difference between Vi plus and Vi minus. Okay, so what is the current through this branch? Let me say this. Okay, for ease, what I'll call this as V1 and this as I1, this as V2, and this current as I2. So what will be I1? I1 will be nothing but minus Gm times V2, right? So whatever voltage is here V2, that will get converted to a current minus Gm times V2, and that current will appear as I1. Similarly, I2 will be minus Gm times V1. Okay. Now the voltage across the capacitor V2, this I2 and I1 have to flow through the capacitances on these two nodes. So by using the relation between voltage and current of a capacitor, I can write C times dV2 by dt. That is, the voltage across this capacitor is V2. So C times C dV by dt is nothing but I2. And similarly, C times dV1 by dt will be nothing but I1. Okay, now I can just put these equations together. What we are saying is now C into dV2 by dt is equal to minus Gm times V1, and similarly C into dV1 by dt is equal to minus Gm times V2. Okay, now subtracting these two equations, what we'll get is C into dV2 by dt minus C into dV1 by dt will be equal to, basically I'm just subtracting these two equations A and B, minus Gm times V1 plus Gm times V2. Okay, let me take this. Okay, so I can write this as C into d by dt of V2 minus V1 is equal to Gm into V2 minus V1. Right? So now I can just collect the terms and to solve this equation as C into d of V2 minus V1. Or let's say delta V is equal to V2 minus V1. So I can write this as d of delta V by delta V will be equal to Gm by C into dt. So how do you solve this? Just integrate both the sides. So what you get? Natural log of minus, what is this? Integral of one. Basically, we are integrating this both these sides, right? So this will be a function of t, and this will be natural log of delta v minus natural log of delta v of 0, right? The initial conditions will be equal to Gm by C into T. So by rearranging these terms, we can write it as delta V will be equal to e raised to, this will be a negative sign, or yeah, e raised to Gm by C into T. Okay, with some proportionality constant which will be dependent on this. Okay, in fact, it will be dependent on the initial conditions. Yeah. Okay, so basically what we get is this K will be nothing but delta V of 0. Okay, so even if you have a very small difference between Vi plus and Vi minus, it will grow exponentially. So if delta V is very small positive value, it will basically grow exponentially and keep increasing in principle forever. But this is a linear circuit. But in our actual approximation, as it reaches VDD, it will get saturated. So that is what happens in this feedback of two inverters, right? So if you have two inverters, okay, if both of these are set up at a slightly different potentials, if this is like yeah, you're right. Yes, that is correct. Yeah. So if you have two inverters connected in positive feedback, and if you set it up at a small potential difference of plus delta V and minus delta V, eventually what the positive feedback will do is, it will, this delta V will produce a negative step here, that negative step will further produce a positive step here, and so on. And eventually it will reach, this will go to all the way to VDD, and this will go all the way to ground. That is what happens. So now the question is, how can we use this positive feedback circuit in a comparator? So what we need to do is, we need to somehow set up a circuit with set up, well, not a circuit. In fact, I want to set up the two inverters in positive feedback with the input voltage. Okay, I need to set up this positive feedback circuit with the initial condition, which is equal to my Vi plus and Vi minus, right? Eventually what I want is, I want to make a comparator, which is this circuit here. So I need, so if I somehow can take this positive feedback circuit of two inverters, initiate it with the two outputs at Vi plus and Vi minus over the common mode voltage. Okay, so it should be basically, if this is the trip point of the inverter, Vm, I need to set this up in such a way that this is Vm plus Vi plus, and this is Vm minus Vi minus. That is what I need to do. So how do you set up the initial voltage? Once you is what is the main crux of the design. Once you set up the initial voltage, you can just release it. It will regenerate and settle to 1 and 0. Okay, so how do you set it up? One simple-minded way would be, you can think is, okay, if I can take these two positive feedback inverters and use two switches, right? So I'll connect this to Vi plus, connect this to Vi minus, again through another switch. Okay, so will this work? It will work, but it will work under some conditions. So what happens in these cases? So what happens in these cases? This circuit will work only if Vi plus and Vi minus can overpower the existing logic value, right? So if this is already at logic 1, if this is already at logic 1 and this is already at logic 0, if you connect this to Vi plus and Vi minus, if this Vi minus is stronger than, so basically what happens here is, this node here is being driven to logic 1 by this inverter. So if your input is supposed to change the output of the comparator, it should be stronger than the inverter which is holding the previous value. So this is something which is not always possible, especially when you want to detect very small signals. So then, okay, we can say, okay, let me modify the circuit a little. Instead of, what I can do is, when I'm connecting the input to this circuit, I can say that I will disconnect the power supply to the inverters. Okay, so in this case, what we will do is, initially we will disconnect the power supply to the inverters, connect the two outputs to Vi plus and Vi minus, so that they take the values of, so that the two nodes take the values of Vi plus and Vi minus. And then once you pre-charge the two inputs to the desired value, you disconnect the input, connect the power supply, and release the circuit. It will regenerate, right? This seems like better than what was done above, because now the input doesn't have to overpower the positive feedback. Okay, so this is something better. But is it still okay? Not quite. What are the problems with this? Remember, in my here, what we had seen is, we need to set up the input in such a way that the two nodes of the positive feedback latch are Vm plus delta V, or Vm plus Vi plus, and Vm minus Vi minus. If you don't do that, what will happen is, you might set up the two voltages which are somewhere in these two locations. Will the comparator work then? May not work that well, may not work at all, we don't know. Okay, so you will get the best performance and quickest decision if you are very close to the trip point and you are at slightly above and slightly below the trip point of the inverter when you release the circuit. If you release the circuit at somewhere other than that, the comparator will most likely still work, but its delay will be much larger, and it may so happen that in the previous value which was stored may overpower this small voltage difference that you have inserted into the circuit, and your logic may actually not be right. Okay, so therefore we need to ensure that the common mode here is close to trip point. In fact, not close to, ideally it should be exactly. Right, you need your common mode to be exactly at the trip point of the inverters. So this is something, the trip point of the inverter will change with process temperature, okay, variations and so on. So it is difficult to establish that exactly. So what is done instead is, this is something which is very difficult to do. So what we do is generally is that we use a slightly different circuit in which we pre-charge both the outputs of the inverter to VDD. So what that is, I will show here. So what we do is, take this inverter circuit, you pre-charge both of these nodes to VDD. Okay, so if I pre-charge both the nodes to VDD, if I look at the butterfly diagram, I'm actually in an undefined state, or what you say, unstable state, right? This circuit has only two stable states. One is at this point and the other one is at this point. This is the metastable state. We will, as I said, we will not discuss too much about metastability in this session. Okay, so what we are doing is, we are initializing the circuit at, or let's say V1 and V2. V1 and V2 both at VDD. So basically we are initializing the circuit at this location, which is not a defined, not a stable state. Right? This is where we are initializing the circuit by keeping both the nodes at VDD. Okay, now what we do is, using two transistors, if we can connect this to Vi plus and Vi minus. These are, what are Vi plus and Vi minus? These are analog inputs which we need to discriminate, right? So this will be some VCM plus delta V, and this is some VCM minus delta V. So once we set this up like this, then what happens is both Vi plus and Vi minus will basically start discharging these two nodes based on the mobility of the transistor. Basically, it will start conducting some current which is dependent on Gm times Vi plus, and this will be Gm times Vi minus. Right? Some small difference between Vi plus and Vi minus, which means that depending on the sign of Vi plus and Vi minus, whether which one is larger, which one is smaller, one of these two nodes will discharge slightly faster than the other. Okay. Notice that when you are having both the transistors, both the inverters outputs at VDD, this amplifier action is not going to take place, because for the when will this amplifier have high gain? It's only when it is close to the trip point of the inverter, right? When you are in that undefined state, the gain of the circuits will be very small, because one of the transistors. So when you have both the nodes at VDD, if you look at it, the transistor level diagram. So this is also at VDD, and this is also at VDD. This is what we are doing, right? So when this is at VDD, this transistor is completely on. This one is off. This is also off, and this is completely on. Right? So any small change in VDD, even if as long as the voltage on these two nodes is more than VDD minus VTP. Okay, as long as the voltage on these two nodes is more than VDD minus VTP, the PMOS won't turn on. Okay, and the NMOS will be completely on. So because of that, what happens is any small change in the potentials of these two nodes between VDD and VDD minus VTP will not have any effect on this feedback network, because the circuit is basically the PMOS are completely off and NMOS are completely on. So there is no change in the state of the circuit for any voltage between VDD minus VTP and VDD. So for V1 minus V2 between this range, the feedback is not active, right? There is no change in the network. Okay, so what happens now here in this circuit is, so I have initialized the circuit with both nodes at VDD, set up the transistors at the input, which will discharge the outputs at slightly different rates. So depending on the sign of input, one of this Gm plus Gm into Vi plus or one of Gm into Vi minus will be slightly larger than the other, and that will result in the node in both these nodes being discharged, right? Both the nodes will start getting discharged. One of them will discharge faster than the other, which is why these two lines are split. Okay, one of them will discharge slightly faster than the other. When the output voltage falls below VDD minus VTP, the positive feedback of the inverter starts getting activated. Okay, for the inverters to start getting activated, the voltage has to drop below VDD minus VTP. So once it reaches close to VDD minus VTP, or when the positive feedback starts getting activated weakly, the moment it reaches close to the trip point, you would have reached a situation in which both the terminals of this positive feedback latches V1 and V2 are at different potentials in the direction which is established by the inputs Vi plus and Vi minus, and they are both close to the trip point of the inverter. Then from here, the positive feedback of the inverter will start getting activated and take the output to the correct value. So this is the sequence of the regeneration between V into the output of the correct logic value. If the Vi plus and Vi minus polarity changes, then what will happen is the node which goes to V1 and V2 will change, but to VDD and 0 will change, but the trajectory will be similar. So now what happens is, even if the common mode of the input is not exactly the trip point, in fact, there is no relation between the trip point of the inverter and the common mode of the input, right? So these two can be set arbitrarily. So the common mode of the input only determines this GM, and it doesn't depend on where exactly the two inverters are, where exactly V1 and V2 are initiated at. Okay, so this ensures that we have proper regeneration of the logic values to logic 0 and logic 1. Okay, so this is the circuit, basics, the heart of the circuit. Now, I have shown this, but how do you actually connect it up in the whole picture? That's very easy. I will just show you the full circuit here. So this is the inverter, one of the inverters. Okay, I have to connect this in positive feedback. So that is what I will do here. Okay, and that initially I need to pre-charge these two outputs to VDD. For that, I will have a PMOS transistor, which will be driven by clock. So whenever clock is 0, this output will be charged to VDD. Okay, so that is established. Second thing is when clock is 0, outputs are pre-charged to VDD. When clock is 1, that's when I should start trying to take a decision of the inverters based on the inputs. So for that, inputs are connected slightly different from what I showed earlier. Okay, it's connected through the source of the inverters itself. So what happens here is and this is of course again driven by the clock. Okay, so when clock is 0, this switch is on, this switch is on, outputs are charged to VDD, this switch is off, which means that inputs have no effect on the outputs and there is no discharge path. So right, so if you look at these two nodes, V1 and V2, when clock is 0, there is no path to ground, but there is a switch which connects the outputs to VDD. When clock goes from 0 to 1, what happens? When clock goes from 0 to 1, the first thing that happens is this switch turns on, the bottom transistor switch turns on, these two switches are off, so the pre-charge is disconnected. Now what happens here in these cases, these two nodes were at VDD. So if I plot V1 and V2, they both were at VDD. They both will start discharging at rates which are different by the difference between Vi plus and Vi minus, right? So one of them will start charging a little slowly compared to the other. When it reaches the trip point of the inverters, which is Vm, the inverter action starts taking over, and one of them will go up and the other one will come down. Right? So this is what happens when clock goes from 0 to 1. In the next cycle of the comparison, once the clock goes to 0 again, the pre-charge gets activated and both the nodes get then charged to VDD. Okay, so this is for clock is 1, and when the clock becomes 0, again it gets pre-charged to VDD. Okay, so in this way, this circuit basically allows you to take the difference between Vi plus and Vi minus by making use of the positive feedback of the inverters. Okay, this is clear, very simple circuit. I've just gone quite slowly over it, but the basic advantages are it allows you to set up the initial conditions on the positive feedback circuit without having to control the common mode of the input to be exactly equal to the common mode of the inverters which are used in positive feedback. Okay, fine. Now the question is, how do we design this circuit? So how would you size the transistors in this? So how will we determine what should be the size of the different transistors? Let us look at it one by one. It's not very difficult, but you just have to understand and draw the equivalent circuit in each of the phases, and then calculate what are the parameters which affect the circuit in that particular phase. Okay, so what are the different phases before I go to the sizes discussion? The different phases are, one is pre-charge phase. Pre-charge phase is the phase when clock is 0. When clock is 0, V1 and V2 are pre-charged to VDD. Okay, so that is the pre-charge phase. Second is what is known as evaluation phase. Evaluation phase is the phase when the circuit evaluates what is the difference in between Vi plus and Vi minus and sets up the positive feedback inverter with that initial condition. So basically, it's the time between the clock going from 0 to 1 and V1 and V2 going from VDD to some small difference close to Vm. Okay, and the third phase is nothing, is the regeneration phase. So this is evaluation. This is regeneration. That is the phase when the positive feedback kicks in and it takes the outputs from the small differential value which was set up across the positive feedback inverter to 0 to VDD. And of course, here you are back to the pre-charge phase. Okay. So that is the different phases of the circuit. So in each phase, we need to see what is the equivalent circuit. And once we look at that, we'll be able to come up with some conditions to what should be how we should size the different the transistors in this circuit. Okay, so let us look at the pre-charge phase first. That's where initially when the clock is 0, the comparator is set up for taking a decision, right? So in the pre-charge phase, what is the equivalent circuit look like? So if I see only this section of the circuit, so what I have is, I have the inverter, there is no path to ground. This is an open circuit here because this bottom transistor is off, so there is no path to ground, and there is a resistance which is pre-charging the output to VDD. So this is R on of the PMOS. So when clock is 0, the PMOS is on, its on resistance is some value R on, and the source of the inverter is basically an open circuit because there is no path to ground from there. Okay, of course, there is the output of the other inverter also, which is connected here. Let me just show it something like this. But this one is also basically disconnected from ground. So basically this node has no drive. It only has a parasitic capacitance. So if I say that the total capacitance on this node is some value, let me say C1 or CA. Okay, the total capacitance on this node will be comprised of the output capacitance of this inverter and the input cap of this inverter. So that will be the total capacitance on that node. So how do I choose my PMOS dimension? So basically, this PMOS transistor, what maybe I'll call it, yeah. Size should be such that the on resistance of the switch is small enough in order to pre-charge this output from 0 to VDD within half the clock cycle, right? So if you are designing this circuit to operate at some clock period, let's say some clock frequency, which gives you some period T clock, when the clock is 0, this duration, within half the clock period, the output should charge from 0 to VDD. So you should design the PMOS transistor such that its on resistance is low enough for it to charge from 0 to VDD. I will not derive the condition, but you can just, if I say that the output should charge to 0.99 times VDD, so 99% of the final value, then you will get a condition that R1 should be equal to T clock divided by 9.2 times CA. Okay, this is very easy to do. It's just a simple RC charging that we do in the network theory kind of basic networks kind of courses. Okay, so if you just plug in that condition of 0.99 times VDD, you will get a condition that R1 should be T clock divided by 9.2 times CA. Okay, so that gives me the size of these two transistors. Okay, next is what about the evaluation phase? In the evaluation phase, how does the equivalent circuit look like? If I draw it here, basically you have the two inverters in positive feedback. And what about the input side? Input side is basically going to look like two current sources which are connected to ground through the R1 of the NMOS transistor. Okay, so this will be some current I and this will be some current I plus delta I, or if I have to say I minus delta I and I plus delta I, depending on the input difference. Okay, so now what should be the sizes of the input transistors and this on and the basically this network which is going to establish the or going to determine the evaluation phase. So now this is a little tricky. So if I choose very large values of geometry for the input transistors, so basically if I see if these are my input transistors M1 and M2, so if I choose M1 and M2 to be very large, then what will happen is I will be large. So basically, what we are trying to say is that the rate at which the outputs discharge V1 and V2 discharges depends on the size of M1 and M2. That is straightforward to see. Okay. Now the thing is, what should be R1? R1 is not very critical, the NMOS transistor here, because it just acts like a source degeneration for the input transistors M1 and M2. So it's a small on resistance which degenerates the source by a small amount. That reduces the gain of the input transistors by a small amount. That's not very crucial. But what is important for us is what is the DC value of I of this I, and what is the transconductance GM. Okay, if the DC current is very large, what it means is that when my comparator goes from the pre-charged values of VDD to the two initial voltages close to VM, what happens is this slope will be large. If the slope is large, what it means is that it will go from VDD to VM very quickly. And if it spends very less time, then what happens is that the difference between the initial voltages Vi plus and Vi minus will be smaller. So basically what it means is that this large current I will quickly bring the voltage close to Vn, which means that there will be not enough time for the input differential to be established. But what happens is, within the half clock period that you have before the next pre-charge phase comes, you have more time for regeneration, right? So basically the size of M1 and M2 determine how much time you will, of course, size of M1 and M2 along with input common mode, determine how much time is spent in evaluation phase. Okay, and t clock by 2 minus that much time will be available for regeneration. So if you spend too much time in evaluation, you will have less time for regeneration. If you spend too much time in evaluation, on the other hand, the advantage you get is you get a proper, you get a larger initial value for the regeneration. So this is something which is you have to simulate and see and decide the sizes of M1 so that you have a good balance between what is the initial voltage that you are establishing across the positive feedback network and how much time you have left for the regeneration to take place. Okay, if you spend too much time if you give too much time for regeneration, then the initial the evaluation will have to happen very quickly, and the initial voltage will be very small, and you will be susceptible to noise. A small noise may end up what do you say, changing the sign of your final decision. So you'll be sensitive to noise if you spend too little time in evaluation phase, but you will get more time for regeneration. If you spend too much time in evaluation, you will be less susceptible to noise, but you will be left with less time for regeneration. So this is something that you need to simulate and design and check so that you are able to resolve the smallest signal that you are looking to resolve. Okay. Third phase is very easy. Third phase is regeneration phase, which is same as what we discussed initially in this when we looked at the where did it go? Here. So third phase is same as what is shown here. It's just two inverters connected in positive feedback, and it will regenerate according to this exponential equation that we have seen. Now, what about then? How do we size the transistors in this inverter? The decision, the size of these inverters should be is determined based on where you want to place the trip point, right? So when I said here that M1 and M2 determine how much time your circuit will spend in evaluation phase and how much time it spends in regeneration phase, there is one more hidden parameter there, because the transition between evaluation phase and regeneration phase happens when your V1 and V2 discharge from VDD to the trip point of the inverter. So it also depends on where the trip point of the inverter is. Right? So how much time you spend in the evaluation phase depends on the size of M1 and M2, which is the input transistor size. It also depends on what is the where the trip point of the inverter is, the inverters that you have designed. Okay. When I say inverters, it is the trip point of these two inverters, right? Because that is where this number will come from. This VM of the inverters, which is where the transition between evaluation phase and regeneration phase takes place. So by designing the circuit and choosing, generally it is advisable to choose the trip points close to VDD by 2. But in this case, because of the presence of this tail current sources, you may have to adjust the trip point so that it is not too high and you don't spend eventually what is the point is that you should spend enough time in evaluation and enough time in regeneration so that there is a balance of speed and sensitivity and sensitivity to noise. Okay, so this is how the simple comparator works. Now the output of this comparator, if you look at output of the comparator, is nothing but V1 and V2. So in the pre-charge phase, it will be pre-charged to VDD, and then they will come down and go back to VDD like this, or come down and relax to go to 0 like this. And in the next phase, again, it will be pre-charged to VDD. Okay, so this is not a proper digital logic. So in order to convert this to a digital logic, what we can do is we can use a simple SR NAND latch. Okay, this is effectively S and Q. So when V1 and V2 are both 1 and 1, the latch will just hold its previous value. When one of them falls to 0, it will either set the output or reset the output depending on which one of V1 or V2 goes from 1 to 0. So by combining the comparator circuit with this latch, you will get a complete circuit wherein the input is a small analog signal and the output is a proper digital logic. Okay, any questions still here? So the circuit is clear. So the total circuit basically is now this first stage, followed by this latch. Okay, so this is the complete circuit of the comparator. Any questions here? The working of this comparator is clear. Then we'll look at some of the problems and improvements over this. Any
Hello,
questions
sir.
about this?
Hello, sir.
Yes.
Sir, above you have drawn two waveforms, red and blue color. So what is the difference? Means red and
One
blue.
of them is V1, the other one is V2.
Blue one is V1.
It depends on what is the size of what is the sign of the input.
Okay.
If Vi plus is more than Vi minus, probably, I mean, V1 may go low. If it's the other way around, V2 will go low, V1 will go to VDD.
Okay.
Okay, so what is happening is both V1 and V2 are pre-charged to VDD. In the evaluation phase, they'll start discharging. One of them will discharge slightly faster than the other till the output reach somewhere close to the trip point of the inverter. Once it reaches that point, the inverter positive feedback action starts and it takes V2 up and V1 down in this case. If it had so happened that the other way around, then V1 would have gone up and V2 would have gone down. Yeah, somebody had a question. What is the use of SR latch? SR latch basically converts this output to a proper logic value. So the output of the comparator, the first stage of the comparator, is not a proper digital logic, right? It looks something like this. This is not a proper digital. You expect a comparator to be either 0 or VDD, but the entire process of decision making takes it to different values of different trajectories. You are trying to use an SR latch to generate a clean digital output from this waveforms of V1 and V2. That is what the SR latch does. Okay, so that is the basic comparator circuit. This is popularly known as, it has many names. Or it's also known as, sometimes known as strong arm latch. Okay, strong arm is the name of a variant of the ARM processor. In one of those ARM processors, in fact, I think this was where it was used first time. This comparator was used and it got its name from there as a strong arm latch comparator. Strong arm is the name of the ARM processor which used this particular comparator as a flip-flop in that particular design.
Sir,
Okay,
I
so,
have one question, sir.
yes.
Sir, you just showed this comparator with input as a voltage.
Yes.
So it's a voltage comparator. Can we use this comparator for a current from a sensor and all? Can we use directly?
As a current comparator, you mean to say?
Yes, sir.
Not directly. It's a little difficult to use this directly as a current comparator, but it is possible to convert that current to a voltage and then use this kind of comparator. Okay, eventually it will require you to convert it to in some way or the other to a voltage. Okay. See, off the top of my head, I can think of something like this. So you have a current sensor, right?
Yes, sir.
So you will definitely need to put it through some kind of diode connected load to detect to basically interface it with other circuits. Now this in fact can be a Vi plus and if you have a differential one, it can be a Vi minus. So
Yes,
this
sir.
can then be connected here, and what you can do is in order to match them properly, you can use a transistor which is connected to clock here also. So then you will have a good match between the mirroring between the input current and the output voltage. See, finally, what does this Vi plus do? It converts this. I mean, what does M1 do? It converts the input voltage Vi into a current Gm times Vi plus, and this one converts it to current Gm times Vi minus. Now, since you have a current, what you are going to do is you are going to take this current and mirror it to this current here. Okay, and similarly, the other side of the differential amplifier. If you have a complementary, what is a differential sensor. So this will establish the difference between I plus delta I and I minus delta I. So something like this you can use to interface it, but you will have to finally convert current to voltage and voltage to current in different sequences. Directly it won't be possible. but rest of the circuit remains the same.
Okay, sir, my idea is like, suppose if we have like programmable comparator kind, suppose if I is greater than this, then there will be separate gain. If I is some threshold, I will keep, and based on that, if I just want to make it as a programmable kind, is it possible with this current as an input, sir?
No, actually, I did not quite understand your question. What is it that you want to do? You want to make a programmable comparator, but programmable in what sense?
But based
What?
on the input current.
So
Suppose
basically, you are saying you want to program the offset.
no, sir, not like that. Suppose based on input current, I want to increase the gain. There, I need a comparator. So
Based
I'm
on
just
input current, you
converting.
want to set the gain of a particular amplifier or something.
Yes, sir. Yes, sir. Next stage, maybe there is an amplifier which is going to amplify this very less amplitude current, and I need to check that current. What is the magnitude of that current? Based on the amplitude, I can set the gain. So is it? It's like the comparator we need. We need to compare the what is
No,
exactly the
actually,
amplitude.
what you are saying is something which is not. What you want is you want different gain depending on amplitude of the input current. So
Yes, sir.
for
Yes,
that,
sir.
what you need is actually you need a amplifier which is known as a compounding amplifier. You don't need. There is something called compounding amplifier. You can just look it up. This is basically a log amplifier. Okay.
Mm. Or a trans impedance amplifier. TIA also it is called.
No. Trans impedance is trans impedance or amplifier. It basically tells you whether the output is in the form of current or voltage. That's all.
Yeah.
There is
Yes,
nothing
yes.
special about that. But
Yes.
compounding amplifier is an amplifier which has different gain depending on the input signal amplitude. So basically, for very small signals, it will have very large gain, and for larger signals, it will have smaller gain. So it will have a voltage transfer characteristic which looks somewhat non-linear like this. Okay, so very small signals, it will have high gain here,
Yeah.
and as
Yes, sir. Yes.
signal amplitude increases, it will have lower gain. So if you have an input which has a very wide dynamic range, and if you want to amplify the lower strengths more, detecting it by comparator and then changing the gain is not the best way to do it. These are standard circuits known as compounding amplifiers. You can just
Okay.
look this up. You can use one of those circuits to achieve the operation that you're looking for.
Okay, sir. Thank you, sir. Good information I got from this. Thank you, sir.
Okay, so coming back to our discussion on these comparators, we'll have about half an hour left, right? We'll look at one of the problems with this comparator. Generally, when you design a comparator like this latch will definitely be required, which means that for the purpose of comparison, you need to generate Q and Q bar, right? But often you will not need to use both Q and Q bar, which means that in the subsequent stage, you may take this Q and connect it to some subsequent digital logic, and you may not use Q bar at all. Now, what happens in that condition is that the delay of the comparator from input to output will depend on what is the will depend on this differential load which is there on Q and Q bar. Okay, let me just take you through that quickly. So I have this circuit here. So this is V1 and this is V2, and this is Q and Q bar. Let me say that I have a load on Q, but there is no load on Q bar. Okay, here the only load on Q bar is let's say the parasitic capacitance which is present on that node. Okay, but my subsequent stages are connected to wherever I'm using the output of this comparator is connected to Q. Now what happens because of that is the delay from V1 to Q and V2 to Q will be different. Okay, why is that so? Let us see. Initially, let's say V1 and V2 are both at VDD. If V2 goes from VDD to ground, if this is at VDD, and V2 goes from VDD to ground, and of course it will pre-charge later. then what happens is, when V2 goes to 0, the output of this transistor, this NAND gate will go to 1. It will go to 1 pretty quickly because it has very low capacitance on the output. Only the parasitic capacitance is there, right? We'll go from 0 to 1, and after that, this one here and this one here will take this to 0, right? And once this comes to 0, this will go to 0, and this will maintain this output at 1. So this will happen through the delay of one inverter with driving a parasitic capacitance and the upper inverter driving the load directly. Okay. On the other hand, if V1 goes from 0 to V1 falls from VDD to ground and V2 stays at VDD, then what happens is this one goes from 1 to 0, but the time taken for the output to change will be now different. It will be dependent on, it will be just the delay of this inverter driving the output capacitance. So in one case, you have the delay of V2 driving the output capacitance, that in turn affecting the output. In the other case, you have a situation wherein V1 directly changes the value of the output Q. Okay, so because of this, what happens is that the delay between one second. Why did this stop? Yeah, so the delay between V1 to Q and V2 to Q is different, which means that when the output of the comparator is changing from logic 0 to logic 1, and when the output of the comparator is changing from logic 1 to logic 0, these two, the clock to Q delay for a 0 to 1 transition and 1 to 0 transition will be different. Okay, so this will basically limits, one of the limitations is that these delays are different, and that mismatch can basically create some problems in determining you will have to take the worst case of these two in order to design this. So can we do something to speed it up? So one of the ways of speeding it up is instead of using a NAND latch, we use a symmetric latch in which you look at the values of S bar and R bar and basically V1 and V2 and generate Q and Q bar directly. So circuit is not very difficult. I mean, all these are digital circuits, so it should be easy to follow. So this is the basic positive feedback network which forms the latch. Okay, just give me a minute. Let me finish this. And this is S. Okay, so somewhat elaborate circuit, and I have here S bar and R bar, which come from the so basically what I have from the comparator is from this comparator I have this S bar and R bar, right? When S bar goes from 1 to 0, the output is set. When R bar goes from 1 to 0, the output is reset. So that was being done by this NAND latch. Now instead of the NAND latch, because of the problems of the differential delay between 0 and 1 transition, we will try to use this particular circuit. So to understand the circuit, let us see what is the steady state. Normally, when the comparator is not taking any decision, S bar and R bar are both high. So when S bar and R bar are both at VDD, this is a PMOS, right? Then what happens is, this, can I use a different, yeah. This transistor is on, R bar is at VDD, so this transistor is also on. If S bar is at VDD, S is 0, which means that this transistor is on. And if R bar is at VDD, R is 0, so this transistor is also on, right? S bar is at VDD, therefore this PMOS is off. R is at 0, since R bar is at VDD, so therefore this transistor is off. Similarly, R bar is at VDD, this is off. S is at 0, so this is also off. So basically what happens is, when S bar and R bar are nominally both at VDD, then this circuit is simply a latch of two inverters. Okay, this part is fine. Now the question is, when one of S bar or R bar goes from 1 to 0 and the other one stays at VDD, what happens? That is what your V1 and V2 do, right? What happens in the case of V1 and V2? One of them drops slightly and goes back to VDD. The other one comes and goes to 0. So let us say the condition when S bar goes to 0 and R bar stays at VDD. So if R bar stays at VDD, what happens is, this transistor is, this transistor is off. If R bar is at VDD, R is at 0, so this transistor is on. R bar is at VDD, R is 0, so this transistor is also off. Right? R bar is at VDD, so this transistor is on. R is 0, this transistor is also on. Now the only thing that changes is the transistors which are connected to S and S bar. So S bar has gone from 1 to 0, so this transistor became on. So notice that S is at VDD, so this transistor is also on. No, 1 second. What did I say? S bar is 0, S is at VDD. So if S is at VDD, this transistor is off. S bar is 0, S is VDD, so this transistor is on. Wait, I did not connect this. Okay, and S bar is 0, so this transistor is off. So if you see, what is happening here is, the paths from VDD to VDD from one of the nodes are activated. So if you look at this node, the path to VDD is activated here. The path to VDD is activated through this network. The path to ground is disconnected. Okay, the path to VDD through this network is also on. Right, and you look at this node, the path through VDD is disconnected. To VDD is disconnected, but to ground is connected through these two transistors. Okay, and the connection from the path to VDD and path to ground are a function of both S bar and R bar, right? So earlier what was happening was, the transition of, for example, in this case, the transition of Q from 0 to 1 and 1 to 0 was determined only by one of V1 or V2, right? That is why the delay was different, because for it to go from 1 to 0, V2 had to had to discharge it by going through this logic path, and for it to go from 0 to 1, V1 did it by going through this logic path, and the number of stages in these two paths were different. But in this case, what is happening is, for the output to go from 0 to 1, it has two paths to VDD. Each of these is controlled by S bar and R bar both. Similarly, for the other output to go to ground, it has two paths to ground, each of which is connected to, which is driven by S bar and R bar both. or SNR. Okay, and similarly the other way around happens when R bar goes low and S bar goes high. S bar stays high. Whatever I've shown in as on here becomes off. Whatever I've shown as on off becomes on. So these two transistors and these two transistors will turn on, and these two transistors and these two transistors will turn off, and the output will change direction. The right side will go to VDD, the left side will come to ground. Now you see whether it is going from 0 to 1 or 1 to 0, the network is symmetric. Okay, so this is what is known as a symmetric SR latch. Okay, so because it is symmetric, its delay from for a 0 to 1 transition and a 1 to 0 transition is identical. What is this? Looks like a full bridge configuration. What is the full bridge configuration? Deepesh, I didn't understand what you're saying. What is a full bridge configuration?
So in our BTEC level, that whenever we have a rectifier configurations, that 4 diodes, that
No, this is I would refrain from drawing parallels between a rectifier and a digital circuit. This is a proper digital circuit. So let us not just because of the positions of the transistors are similar, let's not confuse ourselves.
yeah, okay.
So this is a symmetric SR latch. Symmetric because from S bar and R bar to both Q and Q bar, for both the transitions 0 to 1 and 1 to 0 transitions, the logic depth is identical, which is why it gives you symmetric delays between symmetric clock to Q for transitions of 0 to 1 and 1 to 0. Okay, are there any questions about this? So the basic circuit will look something which is shown here with a different SR latch instead of this NAND latch. Okay, so that is what I wanted to discuss about comparators. We have about 15 minutes left. So, and this is the last session that I am going to conduct. So if you have any questions about whatever topics that I have discussed, we have about 15 minutes. We can have some discussion on that. So what are in the introduction, I discussed the basic MOSFET physics and how the equations of the transistor are derived. In the second session, I discussed fully differential amplifiers. Then sample and hold circuits. Today morning, we saw switched capacitor circuits, and now we have seen comparators. So if you have any questions about any of these, we can just take, if we have 15 minutes, we can keep that for discussion.